On page 342, and this is the square root of x plus 1 equals x cubed. No, it's x squared. X squared minus x. Okay. So very good. The first thing, so we are asked to find a solution. Any solution. I don't care, just one. The first thing we need to do, obviously, is, can anyone walk us through? We need to create a function. So this is the square root of x plus 1 minus x squared plus x equals 0. We are trying to solve the equation f of x equals 0. So this is our function f of x. I'll shut the door. So the next step is, we have to notice that this is a composition of sums and difference of continuous functions everywhere on their domain. So the domain in this case is -1 to infinity, right? So this is on all real numbers, but this requires x plus 1 greater than or equal to 0, greater than or equal to -1. So do not attempt to look for solutions in the graphing calculator for anything to the left of -1. I'm not going to get anything. So I will write number 1, f is continuous on -1 to infinity as a sum or difference of continuous functions. Now with the graphing calculator, I have to find an interval a comma b where f of a is either positive and f of b is negative, or f of a is negative and f of b is positive. And then by the intermediate value theorem, because the function is continuous and it changes sign on the interval, obviously there must be a 0 or a solution of f of x equals 0, somewhere between a and b. So we do have to put this in the calculator. So in y equals, clear. So we put in the square root. In parentheses, you know me. I put parentheses because for many reasons. Number one, you may have an old calculator like I do. This is an old calculator, and most of the time this doesn't work without parentheses under the square root. Actually, it pops up with the left parenthesis already. And secondly, because I don't trust the software that much. Okay, and then minus x squared. And then plus x. I mean, I do, but not to the extent of these parentheses. I'm not sure whether it needs them, it doesn't. That's what I meant. Okay, so I'm going to go to second and table. And I already see that there must be a solution between 1 and 2. Because the function at 1 is a positive number, whatever that is, and the same function at 2 is a negative number. So therefore, between 1 and 2, there must be a solution by the intermediate value theorem. So I write, by the intermediate value theorem, since f of 1 is positive and f of 2 is negative, there exists a c in the open interval a comma b such that f of c is 0. So this is what we knew from a long time ago. From continuity, we knew this theorem. So if the function is continuous on an interval, and it changes sign, it must go through 0 because it's continuous. Okay, so now all we have to do is create Newton's method and decide what is the starting point. So we have to decide on x0, and then this is a function that I like to create like that, which is x minus f of x over f prime of x. We're going to put them in a minute. So now which x0 would you like to start with? So the function is the square of x plus 1 minus x squared plus x. And the derivative is 1 over 2 the square of x plus 1 minus 2x plus 1. So would you like to start with 1 or would you like to start with 2? And this is very important It's very, very important to make sure that the denominator, which is f prime, whatever you choose for x0 is not 0. So if you choose 1, it's 1/4 minus 1. That's fine. If you choose 2, again, it's not 0. So it doesn't matter which one we start with. But we have to make sure that f prime is not 0. So which one would you like to start with? 1. Okay, fine. Now we have to insert this new function in the graphing calculator. Do not delete what you have in there because you already have the numerator. So I'm going to insert the x, I'm going to insert the minus, parentheses for the top and parentheses for the denominator. You don't bother simplifying or trying to simplify anything. There is no need for this situation. So in y equals, do not erase. I have a calculator if you want to use it, it's right here. So insert x minus, put parentheses for the top, continue till the end, put another parenthesis for the entire numerator, and then divide by in parentheses. Be careful how you put that 1 over, 1 divided by, it's in parentheses to the square root. Otherwise the calculator will do something else. So this is x plus 1. Close the parenthesis for under the square root. Close the parenthesis for the denominator of this fraction, 1 over 2 the square root. And then continue with minus 2x, and then plus 1. And close the parenthesis. So one more time, with the graphing calculator, you have to have parentheses around this. I also have parentheses around the quantity under the square root. You have to have parentheses around this. And you must have parentheses around these two. If you don't put parentheses here, the function may be okay. But if you don't write parentheses around the denominator here, or the other option is 1 divided by 2, further divided by the square root. And then you don't need that second set of parentheses, which will be okay. Okay, so I put the Newton's method, the function, in there. So now get out of there with second and quit. Go to variables. Across to y variable. The function is highlighted. Press enter. Yes, press enter again. If you have the function in y1. My function is in y1. Your function could be in y5. So then you have to select y5. And now in parentheses, since we decided that the initial value is 1, so we have 1. And now the next step is I have to copy the entry. So I copy the previous entry, but I have to remove this 1 because I want this number to be instead of 1. So highlight 1, or override if you want, go to second and answer, and then press enter. So this time, the Newton's method is evaluated, the function that we created, is evaluated for 3.18. And then we get 2.22, so we're getting close. So remember, I was expecting an answer between 1 and 2. The first one is a little bit, but the second one is getting close. So the answer has to be somewhere between 1 and 2. Ah, good. 6 decimal places we want. I just copy and repeat. I got 3 decimal places so far. Yes? Huh?
When I go to the when I go to function, once I press this, it goes to
Because you didn't get out of there. You have to get out of there first.
Oh.
If you don't get out of there, you're still in the menu of the table, the graph.
Okay.
Okay, so we got 3 decimal places, and I'll repeat. And I have to record all these. I just wanted to go through it quickly for you to see. So I have 89717, 89717, and this is 9, this is 9. I have 6 digits. I don't need to, this one can be disregarded. So this is the answer, 1.8971795. So the method converged in what, four steps, I think. But we do have to record those. And that's it. Now if you want better accuracy, then you can continue till you get more decimal digits. Of course, the calculator has limitations, however. Yes?
What were you saying about needs to 6 decimal?
Because the problem is asking us to find 6 decimals.
Okay.
So once I see 897679, 897179, and I see those 6 repeat, I don't need the last one. I can already stop.
Okay.
Because they already repeat.
Okay.
There is no point in going to the next iteration. So any questions on Newton's method?
Would you do the same thing for 2?
Yeah, of course. But I would have to find another interval for the next root. Well, I don't know where it is. So it may be between 5 and 6. And then I would choose x0 to be either 5 or 6, and I would investigate that.
Okay.
But the point I was making here is, don't get scared if the first one, even the first 2, are out there because of the tangent. The tangent, depending on which side you start with, the tangent could be outside of the interval. Yes, it did. The first 2 iterations were. But if the answer is positive 3, and then negative 5, and then positive 9, and then negative 3, then you know something is terribly wrong. It must be a max min between the initial value and what you're looking for. It cannot be all over the place like that. Or the function has a trig function in it, and you are in degrees, and you're plugging in 1.3. And they can throw off the whole thing. Or the function is not entered correctly. So as you get closer and closer, or you continue with, you go through sequences of iterations, you know the answer has to be between 1 and 2. If you don't get closer and closer, it's all over the place, you have to stop. Let's say stop. Something is wrong. How did you get that? Everything, all the others? Okay. Good. So are we okay with Newton's method? As I mentioned a long time ago, it's going to take us 15 minutes to present it. So it's nothing. Yes, no?
So 1 is x to the 0, right? It's like x and then 0. So
That's the choice. That's our initial value.
then
Yes.
this took 4 times or 5 times?
4 iterations or 5 iterations, I didn't count, so I can go back and count them. However, it is possible that if you start at the other end with 2, you may get, we say the method may converge faster. Not in 4, but maybe in 3.
Right.
But it's not a big deal, it's not that big of a difference. So it depends. So x sub 0, we also call that x naught, is our choice after we determine the interval. Then from that moment on, it's not our choice. Whatever we get, we have to insert it back into the function.
So then your final answer would be x to the n, and would it be the answer of that
Yes,
or would
but
it be
this
the
will
answer
be
that
x
pops out?
sub 4, x4.
So would you put in 1.8?
Yeah, let me
971.
let me repeat this because I would like to record them. I didn't. I just went too fast. Okay, so our choice was 1, and this is x1. When I click enter, I get, whoa, you can say, wait a minute, I'm expecting between 1 and 2, and what's all this? But that's okay. So this is as long as eventually it converges. Okay, so this is 3.1876726. And now I repeat, but I don't want f of 1, I want f of the previous answer. So I go back and change that to the previous answer, and I press enter. This will be our x sub 2, which is 2.227393. I would have been terribly worried if the second, if x sub 2 would have not gotten closer to 1, 2. I mean, the interval, 1, 2. Okay, so then I repeat. And now I feel much better. So x3 is 1.9322877. And then I repeat, that's what x3. So x4 was 1.8976705, and x5 1.89711795. So I know that once I go to 6, it's going to be the same thing. So I don't care for the last one. But I need to see it to make sure that I have to stop.
So then the answer is
X sub
X is
5.
5,
Yes.
and you don't have to write equals that, or just X
Yeah,
is 5?
yeah. Yes. So that's what I wrote. That's what the solution is. So the first iteration is x1, the second one x2, x3, x4, and x5 I stop. I don't need to write x6. Now, as I said, it's possible that if you start at 2, you may get a solution in 3 steps or 3 iterations, not 5. So it's very possible. Yes, right?
Is there a reason why you're stopping at the 5? Is it?
Because number 6 will be 1,
Oh,
8,
right.
9, 7, 1, 7, 9.
Right, okay. Yeah.
Because we wanted 6.
Gotcha.
If the next one has the first 6 decimals that repeat, I don't need it.
Yeah, okay.
It's this.
Okay.
So the method converts in 5 steps.
Okay.
So since I'm curious now, oh, I didn't mean that. I meant this. So if we start with 2, just real quick, I don't want to waste your time. See, I would have not gotten the. So if I had started with 2 from the very beginning, I would have not gotten that silly 3 point blah 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 and that silly 2.22. So, but we don't have any, we don't have to specific. We're not told that you have to make the method converge in 3 steps or 5 steps. It doesn't matter, as long as you get the solution. So now, so this would have been the first step, and now I want the previous answer. And this is already, so this is x1 and this is x2. So potentially when so it will converge in 3 steps, 4 steps, right? So we had x sub 0, that was x1, x2, x3, and that's 3 steps. So it does matter. The initial value does matter, but it's not a big deal. It's not going to be a huge difference. Okay, so the other question I had, although we will start the review of this if you want today or later. Would you like to see another L'Hopital's rule of any kind? The powers are the most difficult. The products are friendly as long as we make a change in the function to make it turn into a ratio.
Can you do a parallel one?
Yes. I mean, there is a power here if you'd like. I don't know if we did that particular one. But there is a power here on this form. Would you like to do that?
Sure.
Do you all have it? Yes? Okay. So if we want to look at this, so limit e to the x plus x, everything to 1 over x, as x approaches infinity. Do you recall whether we did this problem before? Have we seen this one? No. Okay, perfect. Okay, so we're asked to find this limit, and our first step is to plug it in. We have to plug it in because we have to make sure that this is, first of all, an indeterminate case. It may not be. Maybe the answer is 5, and we're done. So we want to know which indeterminate case in case. That's the situation. And then how to proceed. So when we plug it in, where does this go? Perfect. Where does this go? Okay, so it's an ugly situation as expected. Infinity raised to 0. In other words, we cannot conclude anything. It can be anything. So what would be the next step when we encounter a problem like this? Yes, so first we have to denote the function by e to the x plus x raised to 1 over x. And then indeed, we have to apply natural log to both sides. Okay, natural log y equals 1 over x times natural log e to the x plus x. Okay, so we denoted the function by y. We apply natural log to both sides. We brought 1 over x in front and then natural log of e to the x plus x. Good. So first step we check. Second step we denote the function by y. Third step we apply natural log. What is fourth step now? Apply limit to both sides. That's our next step. So then limit as x approaches infinity from natural log y is limit as x approaches infinity from natural log e to the x plus x. I know that this is not what we are asked to determine. We're not asked to determine the limit of the natural log, but we don't have another way. We have to find this first. Now in this situation, I have to check again and see what indeterminate case, if any, this fits in. So what is this? When I plug in infinity, where does the top go? Okay, let's take it piece by piece. Where does this go? Good. Now picture the graph of e to the x and tell me where does the natural log go? Yes, indeed. So please remember, thank you, Sammy. Please remember this. When x approaches infinity, natural log approaches infinity. And where does this go? Good. So, okay. It didn't take long. It's not a bad situation. It's not too difficult because by simply applying natural log, we changed it into a fraction. So that's nice. And now we can apply what? Yes. So we differentiate the denominator and we get 1. We differentiate the numerator and we get
1 over e to the x plus x times e to the x plus 1.
excellent. Do we agree with this step? So when we differentiate natural log, we have 1 over times the inner function prime, which is e to the x plus 1. Thank you, Jim. Is this okay, everyone? Yes? Okay, I will rewrite and see what happens next. So this is limit as x approaches infinity from e to the x plus 1 over e to the x plus x. If this continues to be infinity over infinity, or maybe 0 over 0, no, of course not, then I continue with L'Hopital's rule. Where does the top go? Perfect. Where does the denominator go? Perfect. So then limit as x approaches infinity, the top. What is it? Excellent. Thank you, Eric. So the denominator? Good. Okay, it's still infinity over infinity. We differentiate again. The top is e to the x, the bottom is e to the x, so the answer must be that. That's it. Thank you. Indeed, 1. So I copy the beginning and I copy the end. I copy the beginning, which is limit of natural log, and I copy the end, which is 1. And then we think. So limit as x approaches infinity from natural log y is 1. Since everything in this situation, they're all continuous functions on their domain, we are allowed, otherwise we would have not been allowed, we're allowed to swap the operators. And now we have to think what this can be. And there is only one number that fits in there. Only natural log is 1. Very good. So therefore, indeed, this has to be e. So indeed, limit as x approaches infinity from 3 pages ago, e to the x plus x, everything to 1 over x is e. So like implicit differentiation, we got the result in a roundabout way, something like this instead of this. Any questions on L'Hopital's rule on powers? Any questions? It's a long procedure. We find out the case, we know the function, we apply log, we apply the limit to both sides, and then we copy the beginning and the end, we swap the operators, and we figure out the number. Okay, so this is what I wanted to review from last time, and then I would like to look at the last section, which is 4.7, optimization. This is a section pretty similar to in variety. I wouldn't say, some problems are cumbersome, yes. So it's similar to 3.9, which was related rates. We can spend a month on it. We don't have a month to spend on it, like we didn't have a month to spend on 3.9 either. So I'm going to select some problems, and then you can select if you want. We are on page page 332. Before we select our first problem, let's see what this really means. We're asked to find max-min of functions. The function may be given to us, which is nice. If I have the function, then I differentiate, I find critical numbers, and I find max-min. Done. But if the function is not given to us, we have to create a function that we differentiate, we find critical numbers, and then we establish max-min. So let's start with a simple example. Let's say 14. Let's read the problem. A box with a square base and open top must have a volume of 32,000 cubic centimeters. Find the dimensions of the box that minimize the amount of material used. So a box with a square base and open top, the volume has to be 32,000 cubic centimeters. Find the dimensions that minimize the amount of material used. Okay. So here is such a box. X, 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 and H. The volume is given to us as 32,000 cubic centimeters. That's all we know. We know that there is a box with a square base, open top, it doesn't have a lid. So the material will be the exterior lateral area plus the base. The volume has to be 32,000 cubic centimeters, and I know the formula for the volume. What is the formula for the volume for such a box?
H times x squared.
Right, the area of the base times the height. Very good. Which I know must be 32,000. So this is what I have for now. The problem is asking us to find X and H that create a minimum possible surface area. In other words, we use the minimum possible amount of metal or carbon, whatever. Okay, so then we have to create a function that represents the surface area, lateral and base. And number two, we have to find its minimum. So can anyone get us started? How do we start by, so let's say we're going to call this S, surface. So what would be the surface area of this box?
X squared plus 4x.
X squared plus 4xh. Would we agree with that? So it's the base, which is x squared. It happens that all sides, lateral sides, are the same dimension. Base times height, x times h, and since there are 4, we have 4 times x times h. Agreed? Well, we do have a minor problem here, and the minor problem is that this function has 2 variables. So I would like to get rid of h somehow. Is there a way to get rid of h?
Is it 4xh or is it 4x minus h?
Times.
Sorry.
Yes, it's based on time. Sorry about that.
Correct.
Differentiate the function by x and treat h like a constant.
Nice try. We have h right here.
Oh. Okay. So this.
So h equals 32,000 divided by x squared, and we have to plug it in. So now I can confidently say that this is finally a function s of x. Is that okay? So this is x squared plus 4x multiplied by 32,000 over x squared. Yes, I will clean it up. I will simplify by 8 and I'll multiply by 4, the numerator, of course. So s of x equals x squared plus 128, I think. No excuse, always check my numbers because sometimes I think of the next step and I may write something else. No excuse. Okay, we're happy now, right? Because we have a function, it has only one variable, we're asked to minimize it. Okay, what will be the next step? So let me refresh your memory, what is this entire chapter all about? 3 applications of differentiation. 1, being able to graph anything. Some of them are difficult, but most of the time, almost everything. Second application, Newton's method, and this is the third one. So what do we do?
Differentiate.
Perfect. So s prime of x equals 2x, and if you took my advice to remember what 1 over x prime is, then we're not going to waste too much time on this.
Negative 148,000.
Very good, thank you very much. And yes, like we did before, I have to simplify this function. X squared, 2x cubed minus 128,000. So I simplified it as much as I could. Yes, we can factor out the 2 if that's what you want to do. It's also true. So 2x cubed minus 64,000 divided by x squared. So let's go back for one more time. So we analyzed what was given to us. We drew a little picture. We presented the volume of that box. Then we created a function. We made sure that the function has only one variable. We differentiated the function. What is next?
Solve for 0.
Yes, set it equal to 0. Perfect. Thank you. Set it equal to 0 and find x. So we are actually looking for critical numbers. This is our next step. That's the reason why we set the function equal to 0. We know that critical numbers come from 2 sources, but if x is 0, then there is no box. So, yes.
How did you get the 2x cubed?
The least common denominator is x squared, so I have to multiply this by x squared because it's over 1.
Oh, right, okay.
So I got 2x cubed minus 128,000, and then I factor out the 2, because now I'm trying to find solutions for s prime of being 0, and only this can be 0.
Okay.
Only the numerator. So then from here, I have x cubed minus 64,000 equals 0. Of course, x cubed equals 64,000. And what will I do?
Cube root.
Excellent. So then x equals 40. And the measurement unit was centimeters. Number 1, I have to determine h. So I determine the base of the square, but I don't have the height. And number 2, I'm only giving you a critical number. You should say, prove it. I mean, how do you know that that x equals 40 doesn't give a maximum instead of a minimum? So I have to show you. So let's find h first. And h was 32,000 divided by x squared. So then this is 32,000 divided by 1,600. So this is 20 centimeters. But as I mentioned, this is not good enough. Oh, I didn't mean that. Okay, so I know that this is 0. So here's our function s prime. You cannot plug in 0, but we shouldn't even plug anything in this. Just for the sake of the sign, this doesn't mean anything. It's always positive. So on the top, I will plug in 0, and I get a negative number. And on the top, if I plug in 100, and I cube it, minus 64,000, this would definitely be positive. So this is typical for a minimum. So now it's guaranteed that 40 comma 20 will give us a absolute minimum surface area for this box. So we will say, if you want to determine it, we can. So S of x, so I will use this because it's easier. So it's x squared, 1,600 plus 4 times 40 and times 20. And that would be the minimum surface area. So what is it? So this is 1,600 plus this is 160 times 20. So is it 3,200? Yes. So I should put here 40 because that's what I plugged in. So S of 40 is 4,800, and it is in centimeters squared, and this is the absolute min. If you deviate from the base, the length of the base, on the side of the base, 40, and the height of 20, you will not, it's guaranteed that you will not find the minimum surface area. If you deviate in any direction, if you say 39, you're not going to get the minimum. If you say 41, you're not going to get the minimum. The minimum is only when x is 40 and the height is 20. Any questions on this? This was our first optimization problem. The function was not given to us. We had to determine the function. We had to differentiate. We had to find critical numbers. And we had to prove that 40 gave a minimum. How? Using the first derivative, the sign of the first derivative. Any questions? Okay. So let's move on to the next problem. And this time I'd like to choose something that has a function in it. Yeah. This caught my eye. So let's read the problem. If a resistor of R ohms is connected across a battery of E volts with internal resistance lowercase r and uppercase R and lowercase r are not the same variable, then the power in watts in the external resistor is this. Okay. If E and R, uppercase E and lowercase r are fixed, but R varies, what is the maximum value of the power? So in this situation, we don't have to worry about the function. The function is given to us. We are only asked to find its maximum. So let's do that. So we copy the function. So this is problem 43 on page 333. And this is the power. And I can write power of uppercase R. So I know that everything else is just noise. Because they're telling us that One more time, they say E and R, E, uppercase E, and a lowercase r are fixed, but R varies, which means this function is a function of one variable, which is the uppercase R. And they're asking us to find the maximum. So one more time, it says, what is the maximum value of the power? So what would be our first step? Say it again.
Is it differentiate?
Of course, of course. P prime of R. Good. Quotient rule mandatory, but not with E squared. Do not bother with E squared. It's a constant. It's a factor in front of R. If I had here, let's say, at the top +2, I would have not been able to do that. But it's just E squared times R. So that's a factor that can wait outside. We don't have to involve that at all. The top prime is good, times the denominator, minus the top, times the denominator prime. So let's differentiate. Remember, our lower uppercase R is a variable. So when I differentiate this, I have to bring the power in front, 2, times R plus R, times the inner function prime. But what is the inner function prime? 1. Excellent. Now the wise thing to do is, like we always did, is to factor at the top and then simplify. That's the best thing to do. You see 2 terms at the top. I see R plus R present in both. I'm going to take it out from the top. So I copy E squared, and then R plus R, and only now, eventually, if you want, I will be able to, or allowed to, simplify by R plus R. But what is left at the top? From the first term, what is left? Exactly. What is left from the other term? This is out. So now I continue. Thank you. Very good. So I have E squared, and this is negative R plus lowercase r over R plus R to the third. Don't bother with this. This is a constant. Now we have to find critical numbers, setting this equal to 0. So critical numbers by P prime of R set equal to 0, but this cannot be 0. So negative R plus lowercase r equals 0, so therefore R must equal
Lowercase.
Good. But I don't know, I have not proved, I have not convinced you yet that this gives a maximum. I have not. So I have to create a table. What if it gives a minimum instead of a maximum? I don't know. That's how I catch my mistakes, right? So we have uppercase R. We have P prime of R. We have lowercase r, 0, and infinity, not really. So at R, the function has a critical number, so P prime is 0 at R. So this is our derivative. Okay? So I will not dare to plug in. So let me just rearrange the function, just for the purpose of plugging it in. This is a waste of time to even try to plug in. So I will replace in that little piece R by 0. The top is lowercase r, the bottom is lowercase r, so the left-hand side is positive. So to the left of r, the derivative is positive. Now let's see what happens to the right of R. Like R is 10R. That's a number to the right-hand side of R. So it's plugging 10R. So the top is negative, the bottom is positive, to the right-hand side beyond the behind the critical number is negative. So this is absolutely typical for a max. The first derivative is positive before the critical number and negative after. So this is a typical situation for a max. Yes, right?
What number did you plug into the left of R?
Oh, I replaced R by 0. And I get lowercase r over lowercase r, which is 1. And to the right-hand side of the little r, I replace uppercase R by 10R. So then I have negative 10R plus R is negative 9R, and the denominator is 10R. And when you simplify, you get negative 9.
Is the 10R the little r? Or is it the,
10 times as much.
okay, 10.
Somewhere as big as I could find it.
Okay.
I said 10 times that.
Okay.
Very good question. So now they're asking us to determine it. So I have to go back and in P of R, replace uppercase R by lowercase r. So now P of little r, I know is the absolute max, and I have to plug it in. E squared times lowercase r over lowercase r plus lowercase r, everything squared. Yes, I have to simplify this. So the denominator is 2 little r, 2r, and I have to square that. What do I get when I square 2r? Very good. And I simplify one of them. So it's e squared over 4r. This is the absolute maximum power. Okay. Any questions? Any questions?
How did I turn the 4 into square?
Because we have r plus r, which is 2r. But when I square 2, I get 4. And when I square r, I get r squared.
Okay.
And then one of them simplifies. Is this better? Perfect. Okay, here's our next. A poster is to have an area of 180 squared inches with 1-inch margins at the bottom and sides and a 2-inch margin at the top. What dimensions will give the largest printed area? So we have a poster and the margins are 1 inches and 2, and the inside is the printed area. What dimensions create the maximum printed area? The top and margins of the poster are, the poster is to have an area of 180 square inches with 1-inch margins at the bottom and sides, and 2 inches margin at the top. What dimensions will give the largest printed area? But we know the entire area that is given to us. The entire area is 180 margins. But what dimensions should we choose? What will the width be? What will the height be of the poster so that we maximize the printed area? So let's give it a shot. I don't know what I did. I clicked something and I should have not. Okay, ready? So this is 34 on 333. So the area, 180 squared inches. And then we have this situation. So we have the area, but we don't know what x is and we don't know what y is. We have some restrictions and we are told that these margins, but we don't know how long should x and how long should y be to maximize the printed area. So how do I start?